Real numbers are an example of an ordered field. But can every field be ordered? Before we answer this question, let's review what it means to be an ordered field. A field F is an ordered field if it contains a subset P such that P is closed with respect to addition, P is closed with respect to multiplication, and for every element X of the field F, exactly one of the three statements is true. X is an element of P, X is equal to 0, or negative X is an element of P. Such a set P is usually called a positive cone. An element X of F is positive if X belongs to P and it is negative if negative X belongs to P. A total order on the field F is then defined by saying that X is less than Y, if and only if Y minus X is an element of P. You can check that the real numbers satisfy this definition if we let P be the set of all positive numbers. Let's go back to the main question. The answer to this question is no, because finite fields cannot be ordered. The proof of this fact is beyond the scope of this video, and I encourage you to look it up. But can every infinite field be ordered? Consider the field of complex numbers. Assume that there does exist a positive coned P in C. The imaginary unit I is not equal to 0. Hence either I belongs to P or negative I belongs to P. Suppose I belongs to P. Since P is closed with respect to multiplication, the square of I, which is equal to negative 1, must also belong to P. Also the fourth power of I, which is equal to 1, is a member of P. But an element and its additive inverse cannot both belong to P. This is a contradiction and thus I cannot belong to P. If negative I belongs to P, then using a similar reasoning we see that the square of negative I, which is equal to negative 1, belongs to P. Also the fourth power of negative I, which is equal to 1, must belong to P. We get the same contradiction as in the first case. That the field of complex numbers is an infinite field that cannot be ordered.